Dear students, in this video we are going to discuss folded dipole antenna, and we'll see what is the difference between ordinary dipole antenna and folded dipole antenna. Ordinary, so see here, this is an ordinary dipole. As you know that this is the ordinary dipole. What is the difference between an ordinary dipole and a folded dipole? Okay, so you know that for an ordinary half wave dipole, the resistance is 73 ohms. But for a folded dipole antenna, the resistance is the impedance is more when compared to dipole antennas. The impedance of the resistance, okay, the impedance of folded dipole antenna, the impedance of folded dipole antenna is more when compared to uh, ordinary ordinary dipole. Okay. So the important, what is the difference? The important modification of conventional half wave dipole, in which the two half wave dipoles have been folded and joined together as shown in this figure. So this, let us consider this is one dipole, this is another dipole. Okay, so one of the dipole is continuous. This dipole is continuous. This dipole is continuous, and the other one is split at the center. Okay, other one is split at the center. Okay, the folded dipole which is split at the center is fed with balanced transmission. So this is the balanced transmission. It is better with the balanced transmission. And as a result, the voltage at the ends of the two dipoles are same. When the radiation fields are concerned, the two dipoles are found to be in parallel. Note that the radiation pattern of the conventional half-wave dipole and the folded dipole are exactly same, but the main difference between these two is that the input impedance, okay, of folded dipole is much higher than that of the conventional half-wave dipole. Okay, so now let us consider we design this very important derivation in this, that is design expressions or design calculation of derivation for input impedance, derivation for input impedance of derivation for, so very important one, derivation of input impedance. Okay, so we solve here derivation of very important one, input impedance, input impedance of folded dipole antenna. Derivation of input impedance of folded dipole antenna. Okay, so let us consider folded dipole means here two dipoles are there. This is one dipole. One dipole is continuous and the other one is, so this is the thing. Okay. Here we are providing the excitation. Here we are providing the excitation. Okay, so see here, let us consider a folded dipole. This is a folded dipole 1 and this is folded dipole. This is dipole 1 and 2 and the distance is lambda by 2. Okay, let us consider the current flowing through this is I1 and let us consider the current flowing through this is I2. Okay, and the separation between distance between these two dipoles are is lambda. Okay, so consider a folded dipole. Okay, so the equivalent circuit are two folded dipole of length lambda by 2. Let us applying a voltage V1. Okay, so at the terminals, let us consider this is 1 dash terminal. Applying a voltage V1, which gets divided equally V1 by 2. I am applying V1, the applied voltage V1 is applied at terminals 1 and 1 dash. 1 and 1 dash. So, which gets equally divided in each dipole has voltage V by 2. This equation can be written as 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 so V1 by 2 is equal to Z11 I1 plus Z12 I2. What is this Z11? Z11 is the self-impedance. Z11 is the self-impedance of dipole 1 and 2. Dipole 1 and 2. Whereas Z12 is mutual impedance. Z12 is mutual impedance. Z12 is mutual impedance between dipoles 1 and 2. Between the dipole 1 and 2. So here I1 and I2 is the current passing through the respective dipoles. If I assume that both the dipoles are having equal radius, both the dipoles 1 and 2 are having equal radius, then I can equate it as I1 is approximately equal to I2. I1 is approximately equal to I2. And similarly, if the separation distance, if the separation between the dipoles, the separation between the dipoles is the order of lambda by 100, then self-impedance can become equal to mutual impedance. Therefore, I can write Z11 is approximately equal to Z2. We can now substitute all this condition, and this condition in this equation. Okay, so what happened now? If I substitute that condition, V1 by 2 is equal to, if I take I1 as common, okay, Z11 plus Z12 into I1. This is why, because we assume that the radius are same. If radius are same, what is the written? I have I1 is equal to I2. Next, what is the thing I have written? V1 is equal to, that is equal to 2 into Z11 into I1. Why? Because the separation is less. The separation between dipoles is less. I can equate it. Self-impedance is equal to mutual impedance. Okay, so therefore V1 is equal to 4 Z11 I. Okay, so I'm thinking that I1 V1 by I1 is nothing but impedance, that is equal to 4 Z11. But if the impedance of a dipole, it is 73. So Z1 is equal to 4 into 73. So the 4 into 73, it is 292. So very, very important derivation. The impedance of a two-way folded dipole is 292 ohms. The impedance of a folded dipole is 292 ohms. This is very, very important. Derivation of input impedance of a folded dipole, it is 292 ohms. Similarly, the same thing, derivation of, derivation for input impedance of tripole. Tripole means, tripole means, what is meant by tripole? We observe here, tripole means it consists of 3 dipoles. This is first dipole, this is second dipole, this is third dipole. Okay, whereas folded dipole means we are having only 2 dipoles. The tripole means it will have 3 three dipoles. Okay, so three, this is the one, two, three. Now let us see what is the impedance of this tripole. Let us see what is the impedance of this tripole. Okay, the same thing. The same thing. If I draw this diagram like this. So this is dipole one. This is dipole two. This is dipole three. If I provided the supply voltage V dash here, what happened? Here also, V1 by 3 will get distributed equally in all three dipoles. Okay, in all three dipoles, the voltage will get divided equally in all three dipoles. So the expression, what is the expression? V1 by 3 is equal to Z11 I1 plus Z12 I2 plus Z13 I3. What is this I1? I1 is current flowing in this dipole. I2 is current flowing in this. I3 is current. Okay. So next, what is the condition we have assumed? If all dipoles are made with, all dipoles are same radius, or same radius, then what is the condition? I1 is equal to I2 is equal to I3. Therefore, V1 by 3 is equal to, I can take I1 copy. It is equal to Z11 plus Z12 plus Z13. What is this Z11? Z11 is the self-impedance of dipole 1. What is this Z12? The mutual impedance present between a dipole 1 and dipole 2. What is this Z13? Mutual impedance present between 1 and 3. Okay. So next, what is the next condition? If the separation distance is very, very less, the separation distance is less than lambda by 100, we can equate self-impedance is equal to mutual impedance. Self-impedance is equal to mutual impedance. Therefore, V1 by 3 is equal to I1 into, I can write it as 3Z1. Okay, so V1 by I1 is equal to, I can write it as 3Z1. Okay, so therefore, next, we bring this V1 Y1 is equal to 9Z11, which is nothing but impedance Z. Impedance Z. This is impedance of a tripole. Okay, right. That is 9 into Z11. So what is the distance of a dipole? It is 73 ohms. That is equal to 657 ohms. So this is very, very important derivation. This is very, very important derivations for a folded dipole. For a folded dipole, the impedance that is equal to 292 ohms. For a tripole, that is equal to 657 ohms. That is equal to 657 ohms. Okay, 657. So depending upon, for example, this is my antenna. Okay, here TV is there. Okay, so we want to provide the impedance matching between this antenna and this TV. Okay, so you are connecting a coaxial cable. Okay, this coaxial cable have various impedances. Okay, so depending upon the impedances, you can select either dipole or you can select a tripole. Okay, whatever the impedance of this one should match with impedance of this coaxial cable. Okay, impedance of this coaxial cable. So this derivation of this formulas is suitable when all the dipoles are having equal radius. All the dipoles are having equal radius. Then you make it another answer. If the radius are not same. If the radius are not same. Means, for example, let us consider this is one dipole and this is my second dipole. Okay. If you observe here, this is this is R1 radius, and this is R2 radius. Here, R1 is not equal to R2. So this radius, the radius of this dipole, the radius of this dipole, so the radius of this, here the radius of this dipole R1 is not equal to the radius of this dipole R2. In that case, it is that folded dipole have the ability of transforming impedance, okay, to the desired value. Okay, so for example, if the cable wire is not, so here as I told that this is my this is my folded dipole, this is my TV. Okay, depending upon the impedance of the cable, the impedance of this cable should match with the impedance of this folded dipole. Okay, so if fixed, if you take two dipole, it is 290 ohms. If you take tripole, it is 657 ohms. But if the impedance is in between this or other than this value, how to get matching to this? Then you can change the radiuses. Then you can change the radiuses. Then the formula is Z is equal to Z11 into 1 plus R2 by R1 whole square. Okay. So Z is equal to 73 into 1 plus R2 by R1 whole square, where R1 is radius of dipole 1, radius of, so this is very, very important form. The radius are not same, then this is the form. Radius of dipole 1, R2 is radius of dipole, okay, radius of dipole 2. Okay, so we can say that the folded dipole have the ability of transforming impedance. For example, if the separation distance also we want to consider, let us consider the folded dipole, this dipole R1, let us consider 1 and 2. This folded dipole 1 and 2 are separated by a distance A, then the impedance formula. If the separation distance is also going to consider, the formula is Z is equal to Z11 into 1 plus log of A by R1 by log of A by R2 whole square. This is the formula. So this is also called as, this is the formula considering for different radiuses and including various radiuses and including separation distance including separation distance. Okay, so there is one factor called impedance transformation ratio, that is ITR is equal to Z by Z11. Is its value 1 plus log of A by R1 by log of A by R2 whole square. Okay, so this is impedance transformation ratio. This is impedance transformation ratio. Impedance transformation ratio is represented with ZR. Okay, so it is represented with ZR. Okay, so if you draw the graphs, this is A by R2, and this is the graph of R2 by R1. So this is for ZR is equal to 3. This is for ZR is equal to 4. This is for ZR is equal to 9. This is for ZR is equal to 8. Okay. So this is the graph which is showing the impedance transformation ratio. Okay. So in this folded dipole antenna, the derivation of input for input impedance of folded dipole. This is very, very important. Folded dipole it is 292 ohms, and similarly, the next one is derivation for tripole. Tripole means we have three dipoles. So 1, 2, 3. Okay, so it is 657 ohms. It is 657 ohms. So if these two impedances are not sufficient, then we can change the radius of the dipoles in order to get the perfect matching between this folded dipole and the cable. Folded dipole and cable. Okay, we'll consider the separation distance also. Okay, so these are all the things regarding folded dipole antenna. Thank you.